Okay, but before that, I want to write one concept that is about the uh, alpha and beta. Let's try to look at in details, right? So just now, we I think in the last sentence of the previous session, we called there are fundamental parameters of the right. Three basic parameters of the transmission line are alpha, beta, and gamma. Anyway, alpha and beta are the most fundamental one. So normally you call them as there is a name for that, the alpha and beta. If you remember, they are called as the line parameters, right? It indicates that you characterize the line's behavior by using alpha and beta. So alpha tells how much uh, attenuation is going to get per meter, right? If you remember, uh, what is the unit for alpha? Again, I'm taking directly this concept from the electromagnetic wave. Same thing we can use here because we are still in the electromagnetic waves only, but related to only certain types of conductors, right? So if you remember, alpha was measured in Napier's or decibels, right? So here also we try to represent the alpha, right? That is measured in Napier's per meter, NEPERS per meter, or you can even write in the decibels per meter. Okay, then you see we have another part that is called as a phase constant, right? So that is beta. It's a constant. You cannot you cannot measure it by using say some unit, right? But if you are able to recall from the basics of waves chapter, maybe we studied that in physics, or even the lower classes, maybe somewhere, maybe up to maybe the plus 12 or somewhere over there, we studied about the waves where we had one relationship, right? uh, to calculate the beta. Do you remember what it is? Right. So it's actually right, we have the it's we had a what you call, it's an imaginary part of our gamma, correct? That's one thing, right? Anyway, uh, normally, right, sorry, normally we write in that way, so you should be able. Hmm. No problem. Anything should be fine, but normally, let us say, uh, it actually represents the distance you take, right? Or it's like say z, there is a z, the z value I have is specific value of z, say z1. Okay, it changes by a wavelength whenever I move, right, further. For example, let me say, let me take a waveform. Okay, so this is a waveform. All right, now say this is my z line. Okay, and now say at a specific point, I'll call this is say z1. Okay, now I add a specific amount of say the distance, that is the lambda itself, right? When I add a lambda to that, I get a similar point, but this z1 is now z1 plus lambda because I covered a distance lambda, right? But now you see, whenever you cover this, what is the amount of phase that it actually got added up? The phase, how much phase shift you have? Is it 180 or more than that? It's it's the same point, right? It's right. That is the 2 pi, right? So normally zero means zero refers to the same point. 2 pi refers to that. 360. Okay, so now the relationship will be something like this. You write beta of, right, like beta into z1 plus lambda, that's the new point, right, minus the beta into the z1 point, same thing we studied in physics. Okay, that's why I'm trying to write it here. That is equal to 2 pi. It's a right. So phase constant into distance, right, minus the phase constant into the original point from where you started. So I think, yeah, it's Z1 plus that. Now you see the beta Z1 minus beta Z1 cancels. You have beta times lambda is equal to 2 pi. So this is the ultimate equation which we used several times, right? So 2 pi by lambda. So that is the equation which we can use to calculate this. Anyway, the alpha equation I'll come back later. As of now, we don't have all the parameters with us to calculate. Okay, but we know how it is present. It is e to the power alpha uh, plus or minus, right? J beta, right? That's what is a gamma whole, the whole gamma is. All right. Okay, so these are the various parameters as of now. So that I'll write one statement. The propagation constant gamma is a constant, is a complex number, and it is the sum of attenuation constant alpha and the phase beta, right? Uh, it's called as a propagation constant because it determines how the voltage behaves on the line. So it's called as a propagation constant. Did I write that somewhere? Yeah, right. We have written here. So anyway, I will not touch that once again. Right? That's fine. So let's proceed further. Therefore, I'll write a final comment about the voltage, that is V of Z. At any point, you can call it as. Now you see, I slightly modify. So I'll write a Vs here. Okay, Vs is the sending voltage. The voltage which I send to the line, e to the power minus gamma Z. Is it okay? Plus, there is a returning component, reflected component, that is VR into e to the power gamma Z. Similarly, you can write the current I of Z is equal to, this is Is into e to the power minus of gamma Z plus IR into e to the power gamma Z. So now this is more clear rather than writing a V1, V2, I1, I2. Right? So what is Vs in this case? This is the uh, voltage sent or sending voltage. What is Vr? This is the reflected voltage. So similarly, you have Is, that is the current sent, right? And I also have IR, that is the reflected amount of current. Okay, fine. So that's the relationship between voltages and currents, right, on a line. Right. Let's move further. The next topic, now we'll derive. I think you asked a question, why do you have a square root for the Z naught equation, right? Yes, yes, yes. I'm going to answer that now. So I'll move on to the derivation part of the characteristic impedance. Right. So if you remember, we had one definition for Z naught, correct? So what was that? I'll just go back and I'll show you. What was the equation for, what was the definition, right, for Z naught? Ah, yes, this is the one you can see. Ah, to the current value at any point, right? That is one definition. Now, since I used one definition already, I'll try to give a different version of that. Assume that the transmission line is very long, okay? It's a very long transmission line. Assume that the length is tending to infinity. Length is very long. Okay. Now, this Z naught can also be defined as the impedance measured from the input side of a transmission line, right? Whenever its length is infinity. Length is tending to infinity. Very long. Okay. So, first let me write, then let's discuss further. Okay. So, okay, character impedance Z naught of a transmission line is defined as, the other equation, other definition we wrote is also right. This is also right. Okay, you can use any one of them if a question is asked about different definition. Okay, is defined as the impedance. Impedance that is measured at the input of the transmission when the length of that transmission line is tending to infinity, right? Anyway, real infinity does not exist. I cannot. But whenever that z is too large, right? Yes, that's the value which we can. Right. So characteristic impedance is measured in that way. All right. Okay. So now let's go back and check one equation. I want to directly start with that equation. I don't want to write everything before that. Actually, you can start from the very beginning of the previous derivation, but I want to use this equation 8. Okay, right? If a equation, if a big mark question comes like 10 marks to derive the characteristic impedance, better you start from the beginning. Okay, that is because it's for many larger marks. Otherwise, if I start from this, actually right now I just want this. Okay, from here I want to start because, right, I already know what concepts I have used, right? So definitely you can add up everything, right? If that's a that question has been asked for more marks. Okay, right? So I'm taking this equation 8 second part. I'll start from there and I'll derive the required equation for characteristic impedance. Okay, so I'll just write here. So we know that directly I'm writing from the equation 8 of the previous part, that is dv by dz is equal to, it is negative r plus j omega l into I, right? Okay, so before I call it by some name, I slightly modify. Okay, what I do, I'll try to write I on one side, take everything to other side. So this implies the current is equal to, yeah, so this is a minus of 1 divided by r plus j omega l. Yeah, this goes to other side. So dv by dz. Okay, fine. So let me call this is right now. So what I know here is I know something, that is the total voltage, but what is V now? V is the voltage at any point on the transmission line. So how do you denote that? That is V, I think called V as e to the power minus, right, plus, yeah. Sorry. Okay, it's a VR into e to the power gamma z. So differentiate, right? I need a dV by dz. So that has to be, right? This is minus of gamma into Vs is a constant, Vs, so minus gamma e to the minus gamma z, plus there is one more gamma coming down into Vr, yeah, Vr into e to the power gamma z. So let me try to write it in this way. What I can do, I can write this as, so I'll take a gamma outside and I'll write the Vr e to the gamma minus gamma z. Okay, so this is equation number 2. Let me substitute, right? So 2 in 1. That means what happens to I now? I is equal to minus of, this is gamma into Vr e to the minus gamma z minus V as e to the, oh sorry, this is positive, minus the gamma z, right? All divided by uh, correct, r plus j omega l. Okay, but I think we have an equation for gamma, if you remember, right? Do you remember? What is the equation for gamma? Other than alpha and right, right, right. But no, that's one thing. I don't want to bring alpha beta here because that's of no use for me. Can you write a R or R and L somehow? Right? So you can see here. So gamma square is equal to R plus j omega L, G plus j omega C. That means R gamma is equal to root of that. Correct? Let me write. So gamma is equal to under root. This is R plus j omega L into G plus omega C. Right? Yes, we use it for that. Okay. Correct, correct, correct. So this is 3, this is 4. Now I put 4 in which one? 3. 4 in 3 gives I is equal to. So anyway, I'll take the minus inside the bracket. Okay. So, and I write root of this is one of it becomes root gets cancelled. That's all. Okay, so G plus J omega C. I'll take a minus inside so that you have, right? This is Vs minus Vs into e to the power uh, minus gamma Z, right? Minus Vr e to the power gamma Z. I took the negative inside this bracket. Anyway, divide this by R plus J omega L. So what happens? The numerator gets cancelled and you get a root here. Hello. Yes, I can hear you. Can you hear? So the numerator term gets cancelled with the denominator, but I get a root in the denominator, right? So we know that comparing this with the Ohm's law, right? The I should be equal to 1 by Z naught times V, right? So this whole thing, the right side is a V now. So this means the Z naught equal to, this implies, so Z naught in the denominator. So whatever is in the denominator becomes the numerator when I, so that is R plus omega L divided by G plus J omega C, right? So that's how you get the Z naught as this equation. Okay, so anyway, we have the other term, other definition as well, which you can use whenever definition is required. But for derivation, this is the procedure. Okay, now the what exactly is meant by the characteristic equation? Oh, sorry, characteristic impedance, right? So you see, the meaning of this characteristic impedance is uh, the value of the load impedance that you need to connect in order to match the load to the given transmission line. It gives you an idea how much, what should be the load that you need to connect, because I have a transmission line. So at any point you measure, there is a Z naught. Okay, there is a Z naught here. It means yes, even at the end, I'm supposed to, right? If you want to match this, right? So the ZL should be equal to the Z naught, right? For matched impedance. So that's the load you need to connect at the input. So, okay. So let me write a point here. This is the meaning of what you call as a characteristic impedance. So we defined it in several ways, but physically, how does it matter, right? That's the first point under this. So the first point is uh, it's the value of mm, load impedance, value of the load impedance. We must connect, right? that's the value which we must connect uh, to the line, right? So that there is a impedance matching, or okay, to the line for matching the impedance, right? In the sense at the end of the line. Fine. Now again, the same meaning. We use the second definition that we use, right? Today we learned something. So assume that this line is very long, right? So that's why I call it as infinite, infinitely long line. Some load might be connected to that. Doesn't matter what load it is. So this is right. The I can say L tending to infinity. The line's length is infinity, close to infinity. In a sense, it's a large. So the impedance seen from the sending end of a very long line is this Z. That means whatever this Zn that we see here, right? So Z in equal to Z naught if L, the length is equal to infinity. So that's the second point. The second meaning of the characteristic impedance. All right. So that means I can write fine. The impedance seen from the sending end of an infinitely long transmission line, right? So length is very large, already we mentioned. So also we can think that the impedance seen looking towards the load at any point on a matched transmission, correct? Because if it is matched, then doesn't matter, right? Anywhere you measure, it's the same. Only when you have non-matching load. So let me say this is the transmission line, right? So you see here, I connect a ZL equal to Z naught. Let's say it is perfectly matched. Then you see anywhere you see inside, you will see the same Z naught everywhere, right? So this is Z naught, this is Z naught, this is Z naught, any point. So that's the most important meaning of the Z naught line, right? So I'll write this is the impedance seen looking towards the load. Under what condition? Towards the load at any point. Let's mention where you are measuring. Okay, at any point on the transmission line. I'll add the point here itself so that this becomes here on the matched transmission line. So that makes more sense. Okay, just put it here on the matched transmission line. So matched means it's understood, right? Yeah, load has to be the load value has to be equal to the characteristic impedance. All right. So whenever you move towards the load or away from the load, doesn't matter. It means the same value of Z. Is it okay? All right. Now let's use this Z naught equation to find out some more equations for which will help us in solving the problems, right? So let us start with the Z naught equation. Z naught is equal to R plus J omega L divided by G plus J omega C under root. Right. Now you see, as the frequencies approach the microwave frequencies, right? From a lower frequency, You keep increasing, right? So that you approach the value of the microwave frequency, like megahertz range, you beyond that, right? As soon as you reach there, you see the omega is very large actually. Okay, the omega value is large, right? So in such frequencies, we whatever transmission lines we use, they are considered as either low loss transmission lines, or they are also referred to as maybe sometimes if it is omega is too large, you will call it as the lossless, because anyway R and G doesn't matter, because omega L, omega C are too huge, right? Those two values are too large compared to R and G. Correct? This is happening when omega is large. Correct? So I'll write one thing. So at or okay, let me write it this way: as the omega increases, this means, right, omega L is much greater than R, and the omega C is much greater than G. So this condition normally happens at microwave frequencies. So normally the transmission lines are considered as the low loss transmission lines, right? That is because you see R is smaller means lesser loss, correct? R is a lossy component. G is another version of R that is also lossy component, correct? Right. So whenever that R value, actually R value is not changing. Omega L and omega C are increasing. So R and G looks like smaller value to you. Right. But still still the concept is like that. Okay. R is lesser, G is lesser. You call it as a low loss line. Okay. Yeah. Whenever R and G are really negligible, it becomes a lossless line. Right. So fine. Anyway, so that means now you see I can neglect R and G, and I can write this implies under this condition the Z naught can be approximated to square root of omega L by omega C. Anyway, omega will also cancel. This is just L by C. So real answer, Z naught is not complex now. So that's why you call it as R naught. Already we discussed this point once. Okay. Let's look at the gamma now what happens, because we know the other parameters also. So this implies at the same time, what is gamma now? Again, gamma is approximated to under root, what is that? R plus j omega L, but it is just, I have j omega L, correct? Perfect. So j omega C. Okay, so I can see j omega into j omega, it goes out as j omega into root LC, right? So this normally, right, I can see that my gamma is only imaginary. Means what? Means what? Means what? This is j beta, right? J beta. So I can see that under this condition. That's why you see there is no attenuation. Alpha is 0 and yeah, beta is equal to, right, omega root LC. Omega root LC, right? Yes, right. This is another reason why we wrote another equation earlier. Let me try to write that. Let me try to, yeah, from this second. Anyway, this is clear, right? There is no alpha, no attenuation, only beta. Fine. Okay, so let's try to do this from the beta equation. I'll try to write what is omega by beta. Take root LC to other side, 1 by root LC. Correct? So this is actually referred to as, right, the omega by beta ratio is actually, if you substitute the omega value as 2 pi f and beta as 2 pi by lambda, right, it's a velocity, but since it is related to beta, it's a velocity only. You are right. But you see, we have a technical name for that. It is called as the phase velocity, because it's measured with respect to the phase constant. So right? Whenever we want to calculate what is the phase velocity, right? Use 1 by root LC to calculate that. Yes, same thing, same thing. No change in that. But the technical term I wanted to bring now, that's all. Phase velocity. Other than that, no difference. Whatever we understood still remains same throughout. Okay, right? So that is about the calculation of Z naught and whatever we can derive from that later. Okay, let's move further. The next topic I want to discuss now is called as the reflection coefficient. Okay, now let's consider the what we understood so far. Let us say there is a line and we call that line is matched if it is terminated with a load that is equal to the characteristic impedance, right? So I'll write that point. I'll start with that. Okay, a transmission line is said to be matched if the load impedance that is, what is that, ZL, let's give a notation now, right? Z load impedance is equal to the characteristic impedance. Correct, the same statement which we used earlier. So that is Z naught. Fine, which means the forward wave is completely absorbed by the load, right? That means there will be only Vs, right? You write the same equation, Vs into e to the power minus gamma, minus gamma Z, right? That's one, it will be there, but there will be no reflected component. Vr will be 0, right? So what do you mean by perfectly matched is that, so far, right, I think we didn't write that, so let's write that. So this implies, right, in the sense whenever you have a matched line, right, the forward wave is perfectly or completely absorbed. Perfectly absorbed by the load, right? Which means what? The reflected wave is 0. That means no reflected wave. I can write VR equal to 0. Okay, but this is again almost maybe the 90% of the time. This is an ideal case. Yes, we can match sometimes. Directly we get the uh, appropriate load value to terminate the given transmission line. Sometimes we get, but as I told, it's a rare case. 90% of the time, that's not going to happen. So in the sense, in a normal life, we can say that, right? Whatever load you connect is different than Z naught. Right. So that means some of the incident wave will be reflected back on the line. Right. So that's the practical case. Let's write that. So this is an ideal case. So I'll write here, but I'll write practically. Practically, the ZL will never be equal to Z naught. This implies what? Incident wave will be reflected back. The incident wave will be reflected back on the transmission line. Now, so what is the magnitude, right? How much you reflect, right? In the sense, I give say 2 volts, that is a Vs. It propagates through the transmission line, reaches the ZL, right? How much the ZL will reflect back? So the amplitude or the magnitude of the reflected wave will fundamentally depends upon the difference between ZL and Z0. It's proportional to that, but not exactly that. It's somewhat right. Yeah, so more difference between Z naught and ZL, more reflection, right? ZL and Z naught are very close, very little reflection. Okay, right. So I'll write that point here, right? The magnitude of the reflection or reflected wave, okay, depends on depends upon the Z naught difference ZL. Okay, this is a difference symbol what I'm using. Z naught difference ZL or ZL, whichever is bigger, you can take it first. Okay, that's right. Anyway, so that's the point here. Now, the amount of reflection caused by the load is expressed in terms of a reflection coefficient, right? That is called as a, now we denote that as a rho here. Okay, so see, this is the notation. It's a rho. Okay, so that's the reflection coefficient. So let's try to define that now. Anyway, we'll try to write it is, okay, the amount of reflection, amount of the reflection caused by the load, right, is expressed as voltage reflection coefficient, right? We denote that as this rho. Right, now let's try to define this. Okay, so it's a simple ratio of reflected voltage to the incident voltage at the load terminal, right? So it is defined as the ratio of mm, the reflected voltage to the incident voltage, where at the load terminal. How much is reflected, you will be able to identify at that point. At the load terminal, we'll be able to identify. Correct? So that's how we'll be able to write. Okay, fine. So let's try to make a derivation here because we want to identify an equation, right, representing this. So because if I simply write what is the total amount of if I directly write rho is equal to say incident wave divided by reflected wave at that point, right? Always we are not having a value for that, right? So I need some other equation to write that. Okay, right. So let's try to write that now. So let, it's a small derivation. Okay, so let the position of the load, right, is Z equal to L. All right, in the sense the load is located at a distance of L from the source. Okay, so that means let me try to draw a diagram. So this is the ZL, and from the starting point of the transmission line, this is located at a distance of L. That's what Z is equal to L. So uh, at this point, right, I have a wave which is coming an incident. It's the incident wave. Okay, so you try to denote that as Vs into e to the power minus gamma into L. Are you okay? Because it is located at a distance L, right? Normally it is Vs e to the power minus gamma Z, but now Z is equal to L, right? So how much voltage is incident on the load? It is equal to this one. At the same time, load will reflect back now. Now let us assume that it's not matched, right? You have a reflecting wave, reflecting wave. Yes. So that is VR e to the power gamma L. Okay. Now, so so we understood what is the meaning of the above sentence. Directly we'll start with what is VL, right? VL is the voltage across this. This is plus minus. I'll measure a voltage here, right? That voltage is VL, voltage at the load. Okay, I'll show you the diagram again. Okay, so this is what I meant by VL. So how do you write VL? So voltage at any point you can use the same equation, right? So that is Vs e to the power minus gamma L plus Vr. No, not minus. Every time it's the same, right? See this equation? It's no, there is no plus minus right now. See the concept we discussed. I'm showing something, right? You see here this one, correct? So the direction of the wave is decided by the z value, correct? Not the plus or minus of v1 and v2. See, this is negative z direction. This is the positive z direction. You see, direction is taken care by that, right? Okay, so I'll highlight again. So you see, these are the terms deciding the direction, not the plus or minus that you write here. Yeah, okay, I understand. Okay, so right now it's not that. Okay, it's a simple sum. At any point on the transmission line, right? How much voltage here, right? It depends upon how much goes here and how much comes here. You do a addition. That's all. Okay, fine. That's why I'm writing this equation, right? That is VR e to the power gamma L. So now you see I took care of the direction. Okay, fine. So as per our what you call definition of I'll hold on to this as of now. So, but let's try to define the rho value. Rho is equal to, it's simply VR by, right, magnitude, that how much ever it's okay. Otherwise, if this might get confused, I'll write it in this way. So this is the reflected voltage by load to the incident voltage on the load. So how do you write that now? So reflected component is VR e to the power gamma L, Vs e to the power minus gamma L. So what I try to do now, I'll take the e to the power to the numerator. So there is VR by Vs e to the power plus 2 times the gamma L. Right. So now I get some idea that this rho is also a complex number. There is a possibility. Okay, let's try to bring it into that concept. We'll understand that later, because as of now I don't see a complex entity directly there indicating J, but it's very clear now because of the gamma being complex, right? Gamma value. So gamma is a complex number, right? Definitely it's going to be a complex. I understand that. But let's try to, okay, let's now I'll call this is equation number 2. This is the 2, right? So as the right hand side of 2, right, indicates that it is a complex, right? This implies I can write, I can expect, I'm expecting rho is equal to magnitude of rho into e to the power j psi. I bring some other constant here, right? Where, uh, let me try to write this psi, I'm expecting this to be the angle of, yes, angle of reflection coefficient. It's obvious that anyway, I see that it is becoming complex. Immediately, I think of writing it in a polar format, right? There is a magnitude and a phase. Okay. Anyway, that's pretty straightforward. Now let's try to write the IL now. So what should be the equation of IL? So also current at the load terminal. That should be the same equation. Vs. It's a voltage divided by what you call the current. Correct? Voltage, load current should be voltage divided by the uh, sorry, impedance. My mistake, I told current. Voltage by impedance. Now impedance is not that of load, right? uh, ZL can be written in that way, but when I try to write the IL at any point on the line, it may be source, the load, or any point on that, you have to use Z naught, because Z naught is the ratio of voltage to current. Correct? Right. So let me try to write that. This IL is equal to, so this is Vs e to the power minus gamma L. Uh, how do I write this now? Do I have an equation for IL somewhere? Let me check. Yes. IL, we don't have anything. Okay, let me just check. Just a second. I'll try to find out one equation, because right now I am not having any equation. Okay, I think I can use one equation which we used somewhere. I directly try to use that. That is, yeah, this equation. This is the one. Okay, so I have this, right? I can use it. So I can call it as Z naught in the denominator, correct? So let me try to write it in another format here, which I am going to use it directly. So this is Vs e to the power minus gamma Z minus Vr gamma Z divided by Z naught, right? I'm using this now. So anyway, at load, it becomes IL, Z is replaced by L. Okay, oh yeah, this is enough for us. So Vs e to the minus gamma L minus Vr e to the power gamma L divided by Z naught. Right. So we have this, right? So this is what is equation number 3. Now let me try to, yeah, I have equation 1 for VL. So how do you write ZL? Therefore, the ZL should be impedance equal to voltage by current, right? I have an equation for VL available. I have an equation for current available. That is IL. So let's substitute. The VL is Vs e to the power minus gamma L plus Vr e to the power gamma L. Okay, just refer. This is the equation. Equation number 1. Okay, okay. I think I wrote L small. I should write small. Sorry. Okay, this is minus gamma L, this is gamma L, all divided by. Now from equation 3, I can write this as uh, this is Vs e to the minus Vr e to the power gamma L divided by Z naught. Right? So yes, as you told, I'll directly bring it to the numerator. So this is equal to Z naught into what we can try to do here. I'll try to take a Vs outside. So this is Vs. And even I take the e to the power minus gamma L out. E to the minus gamma L out. So when that goes out, this is 1 plus this is Vr by Vs. E to the minus goes to the numerator as a plus minus gamma. So there is a gamma L present, and I try to take a minus gamma L means I should add a gamma L. So it is e to the 2 gamma L. Are you okay with this step? You want this is fine? Okay, same thing happens with the denominator. Take a Vs e to the minus gamma L 1 minus Vr by Vs e to the power 2 gamma L. Is it okay? Right. So anyway, this 2 cancels, but I know something. I think we just wrote the Vr by Vs into e to the, that term we wrote somewhere, right? Yeah, equation number 2, right? Vr by Vs e to the 2 gamma L is rho, correct? So this is left hand side is ZL, ZL Z naught into 1 plus rho by 1 minus rho, right? This is the equation anyway. So you can do some mathematics over here to bring the rho into one side, right? Yeah, cross multiply and bring it, right? And you get this equation, ZL minus Z naught divided by plus Z naught is the required equation using which we can calculate the reflection coefficient. So whatever we defined earlier, like we made an assumption, right? It's obvious reflection will definitely depend on the difference between ZL and Z0, correct? We can see that the numerator says that yes, it's a difference, but there is another term ZL plus Z0 coming up. That's because of the all the other parameters in this, right? So what we assumed is correct. We can definitely verify that this is proportional to the difference of ZL and Z0. It's there, it's directly proportional, and we can see.